Hi, this video focused on complete lesson in electric field. See the description of this video. All the useful links related to my other videos are given. Also, by using the playlist of this channel, you can navigate to any video you require. Okay, so in electric field, it's like what should you know in electric field uh, based on exam or focused on exam? What should you know in electric field? Okay, the first point you should know is electric field. What is electric field? You must know that is region where a charge experiences electrostatic force is called electric field. Second, you must know the definition of electric field strength. That is, the strength of the electric field is called electric field strength. What is the definition of the electric field strength? The definition of the electric field strength is electrostatic force per positive Coulomb charge. Electrostatic force per positive Coulomb charge is defined as electric field strength. So if I write it in notation, electrostatic force per positive Coulomb charge is defined as electric field strength. So from this you get the first definition, F equal QA. There also you must know that the positive Coulomb charge should be a point charge. Electrostatic force per positive Coulomb charge, that must be a point charge. That is, from the definition we can say E equal F over Q, F equal QE. The unit of electric field strength is Newton per Coulomb. The unit of electric field strength is Newton per Coulomb. Also you must know the electric field strength is a vector quantity. So how do we define the direction of the electric field? Then you must know that the direction of the electric field strength, how is it defined? Okay, you must know that. How do we define the direction of the electric field strength? Means the direction of the electrostatic force acting on a positive test charge indicates the direction of the electric field strength at a point. So for example, there is electric field in this whole region. If you want to find the direction of the electric field strength at this point, you should imagine if I keep a positive test charge, what's the direction of the electrostatic force acting on positive test charge is the direction of the electric field strength at that point. So how do we define the direction of the electric field strength? The direction of the electric field strength at a point in space is defined as the direction of the electrostatic force acting on a positive test charge. That is the direction of the electric field strength at a point in space. You must know that. Okay, then fourth point, you should know what is test charge. So I told that when I am defining the direction of the electric field strength, I told about test charge. What is the meaning of test charge? You must know that test charge is a tiny charge that do not disturb the existing electric field in the region. Again, test charge is always we use it as a positive charge, positive tiny charge that won't disturb or that will not disturb the existing electric field. That is test charge. You must know that. That is the fourth point you should know in electric field for your exam. Then the fifth point, what thing you should know is Coulomb's law. What is Coulomb's law? You should be able to state the Coulomb's law. Okay, what Coulomb's law says? The electrostatic force between two point charges. So the Coulomb's law is applicable for point charges only. So Coulomb's law says that the electrostatic force acting between 2 point charges, so they are Q1, Q2. The electrostatic force between the 2 point charges, if they are positive charge, they will repel. If they are if they are like charges, they will repel. If they are unlike charges, they will attract. So the electrostatic force between the 2 point charges is directly proportional to both charge and inversely proportional to square of the distance between the two charges. That is the Coulomb's law. Then if you use it, if you combine all, it will become Q1 Q2 over R squared. When you convert into an equation, there will be a constant K Q1 Q2 over R squared. K is called Coulomb's constant. K is equal to 8.89 10 to the power 9 Newton meter squared Coulomb minus 2. That depends on the medium in which the 2 point charges are kept. This is the value for air or vacuum. We treat the air also vacuum because the density of air is much lower. So this is the value for air or vacuum, but different medium, the value of K will be different. Then the K could be related to permittivity of the medium, that is 1 over 4 pi epsilon. Epsilon is the permittivity of electric field. So epsilon for vacuum or air is denoted by epsilon naught. So the epsilon naught, the value of epsilon naught is 8.85 10 to the power 12 farad per meter, where F is the unit farad, that is the SI unit of capacitance. You must know all these things. So the electrostatic force between 2 point charges is given by F equal K Q1 Q2 over R squared, or F equal, instead of K I can use 1 over 4 pi epsilon naught. So the electrostatic force between 2 point charges could be F equal K Q1 Q2 over R squared. We can write that way, or Q1 Q2 over 4 pi epsilon naught R squared. You must know these things, where Q1 Q2 are 2 point charges. Okay, so far we came across two equations. First one is F equal QE. So how do we use this equation? Where do we use this equation? In a space, if you know the electric field strength at a point which is, for example, 10 Newton per Coulomb, the electric field strength in space at a point, and if you keep a charge of, for example, 10 microcoulomb at that point P, if they ask what is the electrostatic force acting on that point charge of 10 microcoulomb, then you can find the electric field strength, electrostatic force acting on that point charge by using F equal QE. You know the Q, which is 10 microcoulomb, 10 into 10 to the power minus 6, and electric field strength 10 Newton per Coulomb. Solve it, you will get the electrostatic force acting on that point. That way you can use it. Or if you know the electric field strength, if you know the electrostatic force acting on a point charge kept at point P, so the electrostatic force acting on a charge of 20 microcoulomb, the force acting on it is, for example, 10 Newton. What is the electric field strength at point P, if the question is? Then we can find the electric field strength at point P. I know the force, electrostatic force acting on a point charge is 10 Newton, and the magnitude of the charge of the point charge is 20 microcoulomb. Then I can find it by using E equal F over Q. Force I know 10 Newton over Q, 20 microcoulomb, 20 into 10 to the power minus 6. Solve it, you will get electric field strength at point P. So we can use this equation to find these two things by using a point charge Q, and if you know the electric field strength at a point in a space, right? That's the application of this equation. Second, we learned the Coulomb's law. F equal K Q1 Q2 over R squared. The second equation we learned is F equal K Q1 Q2 over R squared, or Q1 Q2 over 4 pi epsilon naught R squared. If you know the 2 point charges and their charge and the distance between them, we can find the electrostatic force between the 2 point charges by using this equation. Okay, then what should you know the other point? The sixth point that you should know, When a point charge is kept in space, it will create electric field around it everywhere. What could be the strength of the electric field at a distance r from the point charge? You should be able to derive the equation for that. So imagine in space a charge q is kept. What could be the electric field strength at a distance r from it at point P? Okay, they can ask you to derive the relevant equation. You must know that. Imagine if I keep a positive test charge at point P, then the electrostatic force acting on the positive test charge, which is given as F, according to Coulomb's law, the electrostatic force acting on the positive test charge, delta Q, is equal to F equal K Q delta Q over R squared. The electric field strength at point P is defined as electrostatic force per positive Coulomb charge. So I know the electrostatic force acting on the point charge kept at P, which is KQQ over R squared. So KQ delta Q over R squared divided by delta Q. That will give the strength of the electric field or electric field strength at point P. So here delta Q and delta Q will get cancelled. So it will become KQ over R squared. That is the next equation you must know, that gives the electric field strength produced by a point charge Q. Point charge Q, how it varies with distance from it. So K is a constant, Q is a constant. So from this equation we can say E proportional to 1 over R square. This relationship is called inverse square law, you must know. So if you plot a graph of electric field strength produced by a point charge, remember that point charge against the distance from it R, the graph will be inverse square law like this. So if I take two different points or three different points, this is R1, R2 and R3. Electric field strengths are E1, E2, E3. So they can give a graph like this and ask you to check whether the graph obeys inverse square law or the electric field strength obeys inverse square law. So take three clear coordinates from the graph. So find E1 R1 squared, E2 R2 squared from the graph, E3 R3 squared. Find their numerical values. If they all are same, exactly same, you might not get practical. But if they are almost equal, they all are equal, then I can say the electric field strength obeys inverse square law. They can ask you to check in the paper whether the electric field strength created by a point charge obeys inverse square law. Then next you must know, if you plot a graph of electric field strength against 1 over R squared, E equal KQ over R squared. This could be written as KQ into 1 over R squared E. So this is why the KQ could be taken as gradient M. 1 over R squared could be taken as X. So if you plot a graph of E against 1 over R squared, the graph will be a straight line through the origin. The gradient gives K times Q. You must know that. Okay, so the next point you must know is electric field, the electric field lines. Okay, what electric field line indicate? The electric field line indicates the resultant electrostatic force acting on a positive test charge kept at that point, or the electric field line indicates the direction of the acceleration of a positive test charge kept at that point. Again, I am telling, electric field line indicates at a point, indicates the direction of the resultant electrostatic force acting on a positive test charge, or the electric field line indicates the direction of the acceleration of a positive test charge. Don't say it indicates the direction of motion of a positive test charge is a wrong statement. Don't say direction of motion. It indicates the direction of the resultant electrostatic force acting on the positive test charge, or direction of the acceleration acting on positive test charge, not the direction of the motion of the positive test charge. Remember that, not the motion. Okay, for example, if there is a positive point charge, the direction, the electric field lines, if I keep a positive test charge here, it will experience resultant electrostatic force away from it. So the direction of the shape of the electric field line will be this way. The direction is away from it. That's the way the direction of electric field lines is defined. The direction of the electrostatic force acting on a positive test charge. So like that, I can draw different lines around it. How many lines should I draw? For that, we should know the properties of the electric field lines. You must remember, first property, electric field lines never cross each other. Electric field lines never cross each other. Second property, the electric field lines always start from positive charge, or they always move away from the positive charge and move towards the negative charge. Why do they move towards the negative charge? The definition, because if there is a negative point charge, if I keep a positive test charge here, the positive test charge will be attracted by the negative point charge. So the direction of the electric field line at this point will be towards it. So but when we draw the electric field lines, they should be always towards the point charge. So first property, the electric field lines never cross each other. Second property, electric field lines always move away from the positive charge and move towards the negative charge. Third point, the number of lines per unit area indicates the strength of the field. So it's like that. When you compare two different point charges, this is a point charge, there's another point charge, this is negative charge, doesn't matter, but this negative charge has higher strength. Both are point charges. This, for example, this is 4 microcoulomb, this is 1 microcoulomb. So I know that this has the strength is more, the field strength is more because its charge is more. So there, when I draw both, I should draw more number of lines on this charge because higher strength compared to this charge. So when we draw, all the length of the lines should be almost eye level same. So the number of lines per unit area indicates a strength. So here, stronger field compared to this, because 4 microcoulomb, this is 1 microcoulomb. This type of field line is called radial field. Radial field means in which the field lines appear to be converging towards a point or diverge from a point. That type of electric field pattern is called radial field. In radial fields, the strength of the field depends on the distance from the point charge, or inversely proportional to square of the distance from the point charge in radial field. Okay, so we must know the shape of the electric field when there are 2 point charges kept in space. So when 2 point charges are kept closer to each other such that the field produced by each point charges overlap with each other. So the field pattern what you see in that region will be the resultant or outcome of the overlapping of the field line. So you should be able to draw the resultant field pattern when there are 2 point charges kept in space. So I'll draw them now. So when there's a positive point charge and a negative point charge kept in space, and if I keep a positive test charge here, this will repel, this will attract, so the field line will be from positive to negative. When I keep a positive test charge here, this will repel, this will attract, but this point is closer to positive charge, far away from negative charge. So at this point, the resultant force will be somewhere here. When I keep another thing about another point here, this will repel, this will attract, so this will repel like this. This will attract towards it. So the resultant force will be somewhere here because this point is closer to positive charge, far away from negative charge. So this repulsive force will be stronger than attractive force. So the resultant will be more closer to repulsive force like this. So like that, if I imagine each and every point in this space, and if I connect all those points, that will appear like this. So if you want to find the direction of the electric field strength at this point, you should draw a tangent at that point. The tangent indicates the direction of the resultant force acting on that point, or indicates the direction of the electric field at that point. Same way here it should be like this. When the charge, you can see the field lines are more closer near the point charges. When they move away, the gap will increase. Like this, you can draw more point charges, more positive lines like this. Right. Same way, when there are two positive charges kept closer to each other, what could be the shape of it? There's a point. Forget about this. Now, completely new diagram. 2 point positive charges are kept next to next. What will happen? When I keep a point charge here, this will repel, this will attract. So there won't be any field lines here. But when I consider this one, this will repel this way, this will repel this way. The resultant force I need to consider, it will be somewhere here. So the resultant field pattern will be something like this way. They'll point away from it like this. The field lines never cross each other. Like that. So in the center part, there will be a point where there is no electric field lines, no electric field strength will be equal to 0. That is called null point or neutral point. Here also, if you draw a tangent at a point on the field line, that indicates the direction of the resultant electrostatic force acting on that at that point, or direction of the electric field strength at that point could be found by drawing a tangent at a point on the field line. Okay, so I already told that about radial field. Radial field is produced by point charges. So in which the field lines appear to be diverging from a point charge or converging towards a point charge, in which the strength of the field obeys inverse square law if the radial field is only just due to one point charge. So the strength will be different at different distances from the point charge. So the other type of field is called uniform field. Uniform field means the field lines are parallel to each other with equal space. That means the strength of the field is the same at all points. That is the uniform field. So in uniform field, the strength of the field is the same at all points. That means the electric field strength is the same at all points. Means we told that the property of one of the properties of the electric field is it indicates the strength of the field. Number of lines per unit area indicates the strength of the field. So in uniform electric field, the strength of the field is the same at all points. Means the uniform field So in uniform electric field, the field lines are drawn with equal space and parallel lines. We'll come across later how to create uniform electric field. Actually, by using, you already studied oppositely charged parallel plates. In the region between the oppositely charged parallel plates, you will get uniform electric fields. The field lines are parallel with equal space. So if you draw a unit area, wherever you draw unit area, the number of lines passing through it will be the same. So strength is the same. Okay, so then there could be calculations, questions related to these equations. The third equation also I write, that is E equal KQ over R squared. I derived it, or Q over 4 pi epsilon naught R squared. That indicates how the electric field strength of a point charge q varies with distance r from it. Okay, so based on that there could be a question something like that. ABCD forms a square. The length of a side is 10 centimeters, so these are 90 degrees. The question could be find the electric field strength at point D. So it's a square. On the corners there are 2 point charges kept. At A there is a plus or positive 10 microcoulomb. At point C there is negative 6 microcoulomb. The question could be find the electric field strength at point D, means you need to find the magnitude of the electric field strength and the direction of it. Okay, so I am not going to solve it. I'll tell you how to do. I already discussed in my I already did electric field. There are 12 lessons. So there I discussed it. So it's a revision. So I'll show how to find the direction of the resultant electric field strength at point D. Okay, so we know electric field strength is a vector quantity. We need to find the electric field strength at D due to positive 10 microcoulomb and negative 6 microcoulomb separately. Okay, we'll say the electric field strength produced by positive 10 microcoulomb at D is E1. What could be its direction? Because electric field strength is a vector quantity. So there, for that I already defined how to find the direction. Imagine if I keep a positive test charge at D. If I keep a positive test charge at D, that will be repelled by positive 10 microcoulomb. So the direction of the electric field strength at D due to 10 microcoulomb will be this way. Let it be E1. Same way, if I keep a positive test charge, 6 microcoulomb will attract. So the electric field strength at D due to 6 microcoulomb will be towards it. Let it be E2. Find E1 and E2 separately by using this equation, E equal KQ over R squared. So E1 is equal to KQ over R squared. K, that is 8.99 10 to the power 9. Q is 10 microcoulomb, 10 into 10 to the power minus 6 over R squared. This is 10 centimeter. So 0.10 squared. Find the E1. You will get it. I am not solving it. Same way, find the E2. So find the E2 by using the same equation. E equal KQ1 E equal KQ over R squared. So that is 8.99 into 10 to the power 9. I already found the direction. That will be towards right, because if I give a positive test charge, negative 6 microcoulomb will attract it. So the electric field strength at D due to my negative 6 microcoulomb is towards right. So 8.99 10 to the power 9 into KQ. Our Q is minus 6 microcoulomb. We don't put the minus sign because already I found the direction, that is towards right. So just put 6 into 10 to the power minus 6. Don't put minus sign, not necessary, because I already found the direction by imagining keeping a positive test charge over R squared. The distance of 6 microcoulomb from D, that also 10 centimeter, convert to meter, divide by 100, 0.10 squared. Find the E2. So you know the value of E1 and E2. So E1 and E2 are among them 90 degree because the lines, it's a square. So use the Pythagoras theorem. So you know the E2 this direction, you found it from here. You know the E1, that is this direction, you know that. Among them they are 90 degree. So unit 1, vectors, how to find the resultant. You can use Pythagoras theorem. The resultant vector will be this direction, ER. You can use the Pythagoras theorem. ER squared is equal to E1 squared plus E2 squared. You will find it. And also they can ask you to find the direction of the resultant electric field strength theta with the side DC. So this is horizontal E2 along the side DC. So theta will be equal to tan theta opposite, that is the E1 in this vector diagram, E1 over E2. From that find the theta, you will get the final answer. Okay, so another question based on the same equation. 2 point charges, 12 nanocoulomb, 12 nanocoulomb, both are positive charges, kept 8 centimeter apart. P is a point at a distance of 10 centimeter from this point charge and 10 centimeter from this point charge. They can ask you to find the resultant electric field strength at point P. Okay, so we know how to find it. If I keep a positive test charge at point P, this will repel. So the direction of the electric field strength is E1 equal KQOR squared. So Q is 12, distance is 10 centimeter. So E1 along this line. Same way, when I keep a positive test charge, this 12 nanocoulomb will repel. So the direction of the electric field strength due to 12 nanocoulomb at this point will be along this point. That also E1, because both have the same magnitude of charge and both are at the same distance from the point P. So therefore E1 is equal to E2. Okay, so if I resolve them, so I need to find the resultant electric field strength at point P. So they are at two different directions. They make an angle theta, equal angle with horizontal line. We can find the theta, it's not an issue. But if I resolve E1 sine theta, this is E1 sine theta downwards, this is upwards. So the vertical components will cancel each other. So the resultant electric field strength is going to be at point P towards right. That's going to be resultant ER is going to be 2E1 cos theta. So E1 I can find, E1 is equal to, anyway both are at the same distance from point P. E1 is equal to KQOR squared 8.99 10 to the power 9. One of the Q I am finding for this E1 means 12 nanocoulomb, 12 into 10 to the power minus 9 over R squared, 10 centimeters, 0.10 squared. I can find the E1. How to find the cos theta? So in this right angle triangle, we know the opposite side. This is 4 centimeter, this is 10 centimeter. If I want, I can find the sine theta. Sine theta is equal to opposite 4 centimeter or hypotenuse, that is 10. So from this I can find the theta. Use the theta here with cos theta. You will get the resultant electric field strength. Nothing, that will be the electric field strength at point P. Like that, there could be questions for point charges in different geometrical shapes. Anyway, finally, you are going to use the geometry and maybe Pythagoras theorem, or you are going to resolve everything based on unit 1. But only thing, you should be able to find the direction of the electric field strength at that point due to different charges. For that, imagine if I keep a positive test charge, what could be the direction of the electrostatic force acting on the positive test charge due to a particular charge given in that diagram. One by one, check it. Finally, use the unit 1 idea, finding the resultant. Okay, so the next point you must know is null point or neutral point. So what is null point? The point at which the resultant electric field strength is equal to 0. The point at which the resultant electric field strength equal to 0 is called null point or neutral point. Also, you must be able to calculate the distance of a null point from a point charge when there are more than one point charges kept in space. For example, there are 2 point charges kept. This is P at point P. There is 10 microcoulomb positive point charge is kept. So there is another point Q at which negative 16 microcoulomb point charge is kept. Distance between P and Q is 12 centimeter. The question is, find the distance of a null point from P. So first you should be able to identify or determine the null point. Where could it be? So it could be either between P and Q, or on the right side of Q, or on the left side of P, or either up or down. Somewhere there could be null point. Can there be more than one null point? Okay, we'll analyze it. Okay, null point means the point at which the resultant electric field strength must be equal to 0. Imagine if I consider a point somewhere here, the direction of the electric field strength due to 10 microcoulomb will be this way, because I should imagine if I keep a positive test charge at this point, then the direction of the electric field strength due to 10 microcoulomb will be this way, E1. The direction of the electric field strength due to minus or negative 16 microcoulomb will be this way. So these two electric field strength never cancel each other because they two vectors in different angle. Unit 1 again unit 1. There are E1 and E2 are two vectors. If two vectors wants to cancel each other, they should be on the same line, opposite direction. So E1 and E2 never cancel each other. So there can't be a neutral point below the line PQ. Same way there can't be a neutral line above the line PQ. So the possibility of neutral point is somewhere on the line PQ, should be on either side, between PQ or either side, on the right side of Q or on the left side of P, will determine. Right. So can there be a null point between P and Q? Okay, if I think about just a point here at this point, okay, can there be a null point between P and Q? If I keep a positive test charge, because I want to find the resultant electric field strength, that means I should determine the electric field strength due to minus or negative 16 microcoulomb and positive 10 microcoulomb, whether they can cancel each other. So if two vectors want to cancel each other, we know they should be on the same line, opposite direction, same magnitude. Okay, that is unit 1 idea. So if I consider a point here, the electric field strength due to 10 microcoulomb, if I keep a positive test charge, it will be towards right, E1. The electric field strength at this point due to negative 16 microcoulomb, if I keep a positive test charge, it will attract that also towards right. So E1, E2 both are in the same direction. So there can't be a null point anywhere between P and Q, there won't be. On the right side of Q, we'll think about a point somewhere here. Okay, if I keep a positive test charge, 16 microcoulomb will attract it. So let it be E1. The plus positive 10 microcoulomb repel it, let it be E2. So they are in opposite direction. Can they cancel each other? We'll see. E1 is due to negative 16 microcoulomb. So E1 is going to be K 16 10 to the power minus 6 over distance. If I say this is x, the distance of the null point from Q is x, it's going to be x squared. E2 is equal to K into 10 microcoulomb, 10 into 10 to the power minus 6 over the distance of P from the point, what I consider the point, let it be N. The distance of P from N is equal to 12 plus x, or I can convert to meter. I can keep it in centimeter, it's not an issue. 12 plus x all things squared. Can E1 equal to E2? They are in opposite direction, but if they want to cancel each other, they should have the same magnitude. Is it possible? No, because when you consider the numerator, K is the same, 16, 10. So 16 is greater than 10. So the numerator of E1 is larger. Again, consider the denominator, x squared, 12 plus x. Again, this is larger. Denominator larger, numerator smaller. Here, numerator larger, denominator smaller. So clearly we know E1 greater than E2. So on the right side of Q, there won't be a null point. So from that I can conclude there can't be a null point on the right side. Okay, we'll see the last point. On the left side of P, consider a point N, distance x. So if I keep a positive test charge, 10 microcoulomb will repel it. So E1 to the left, minus 16 microcoulomb attract it. So E2, yes, here also at point N also, the two electric field strengths are in opposite direction. Can they have same magnitude? Yes, we'll see, because E1 is equal to K into 10 to the power minus 6 over x squared. E2 is equal to K into 16 into 10 to the power minus 6 over x plus 12 squared. Yes, here there can be, because here numerator smaller than this one, denominator also smaller than this one. So E1 can be equal to E2. They are in opposite direction, so they could cancel each other. So the null point is on the left side of P at a distance x. Okay, so if it is a null point, E1 minus E2 must be equal to 0. So that is the resultant electric field strength, which is E resultant, must be equal to 0. E1 minus E2 k into 16 into 10 to the power minus 6 over x plus 12 all things squared must be equal to 0. Okay, now maths, physics over, solve it, take it to the right side. So k will get cancelled, 10 to the power minus 6, 10 to the minus 6 get cancelled, 10 over x squared is equal to 16 over x plus 12 all things squared. Take square root on both sides. So square root of 10, that is 3.16. 3.16 over x is equal to 4 over x plus 12. Okay, physics over maths, cross multiply and solve it. You will get x is equal to 45.14 centimeter, because I keep the 12 in centimeter, so centimeter. So the null point will be at a distance of 45.14 distance centimeters from P on the left side on the same line of QP. Okay, so far we came across point charges. This equation could be used only for point charges. But when we have a metal sphere, that is conductor, if it carries a uniform distribution of charge on its surface, when you charge a metal, the charges will stay only on the surface, not inside the metal. So when a metal conductor carries a uniform distribution of charge on its surface, then we can use the equation E equal kq over r squared for the metal sphere. There, Gauss law is not in your syllabus, but we should assume the whole charge, the total charge, uniform distribution of charge on the surface, if it is Q, we can assume the whole charge is concentrated at the center, but it's not actually. But according to Gauss law, we can assume the whole charge is concentrated at the center, and we can use the equation E equal kq over r squared. So inside the metal sphere. So when it comes to metal sphere, it's not a hollow sphere, it's a solid sphere. The all part, it consists of metal. So inside the metal, the electric field strength is equal to 0. There could be a question, why the electric field strength inside the metal is equal to 0? The answer, it carries a static charges. So static charges means they must be at rest. So if it has a electric field inside, the charges will experience, charges means the delocalized electrons, or charges will experience force and they will move, but they won't move because they are static charges. Therefore, the electric field strength must be equal to 0. We can say the electric field strength 0 because static charges won't experience force. If they experience force, they will move, then they won't be static charges, but they are static charges, so they should not experience any electrostatic force. So electric field strength must be 0 inside the metal sphere. So there can be a question something like this: the radius of the sphere is equal to 4 centimeter. First question they can ask, what is the electric field strength, how much, at 2 centimeter from the center O. O is the center. From O, what is the electric field strength, they could ask. So that we know the answer, the electric field strength inside the sphere is equal to 0. I already give the explanation. Second, they can ask, there is a point P on outer surface. The distance of the point P is 6 centimeter from the surface. Find the electric field strength at P. So E at P, which is at a distance 6 centimeter from the surface, means it is at 10 centimeter from the center. We assume the whole charge is concentrated at the center according to Gauss law. So the electric field strength at P is equal to kq over r squared. We can use by assuming the whole charge is concentrated at the center. We can assume the whole charge is concentrated at center only when the charge distribution is uniform on the surface. So E equal KQ over R square. K is equal to 8.99, 10 to the power 9. Q, the whole charge, if I say the charge of the carried by the sphere is equal to 10 microcoulomb, then 10 into 10 to the power minus 6, we assume it's concentrated at the center, that is the total charge on the surface, divided by R squared. From the surface, point P is at 6 centimeter. We assume the whole charge 10 microcoulomb is concentrated at the center. So from the center, the distance is 10 centimeter. So that is 10 into 10 to the power minus 2, all things squared. Solve it, you will get the electric field strength at point P. Okay, so next thing is electric potential created by a point charge. Electric potential created by a point charge. How it is defined? Say if there is a charge Q kept in space, what is the electric potential of this charge at point P? How do we define the definition of the electric potential of charge Q at point P, which is at a distance r from the point charge? So the electric potential is denoted by V. How do we define? It's defined as the work done in moving plus 1 coulomb or positive 1 coulomb charge from infinite distance to point P is defined as the electric potential at point P. Again, I am defining the electric potential at point P, which is created by a point charge Q, is defined as the work done in moving positive 1 coulomb charge from infinite distance to point P. The total work done is defined as electric potential at point P. So there actually we need to integrate, not in your syllabus, but final equation is in your syllabus. So the electric potential at point P is defined, given by V is equal to KQ over R. You must know that. So that is the next equation. V, electric potential created by a point charge Q, is given by KQ over R, or Q over 4 pi epsilon naught R. So there, when we are using this equation, we must include the sign of the charge Q. Remember that we must include the sign of the charge Q. Also, V is a scalar quantity. Its SI unit is volt or joule per coulomb. Again, I am telling, when we use the equation, we must include the sign of the charge Q, because if it is a negative charge, the electric potential created by a negative point charge will be a negative. Positive point charge will create a positive potential. Negative point charge will create a negative potential. When we are using this equation, we must include the sign of the charge. Normally R must be in meter, so the unit of volt, electric potential, is volt, SI unit, or we can say joule per coulomb. Okay, based on this equation, there could be questions like this. There's a point charge 10 microcoulomb, positive 10 microcoulomb is kept in space. Find the electric potential at a distance of 12 centimeter from point charge at point P. So the electric potential V equal KQ over R. So 8.99 10 to the power 9. Q is 10 microcoulomb, 10 into 10 to the power minus 6 over 12 centimeter, 0.12 meter. Solve it, you will get the answer, that is 7.49 10 to the power 5 volt or joule per coulomb. Okay, so the next question, there's a point charge, negative 15 microcoulomb. Find the electric potential of this point charge at point P, which is 10 centimeter away from this. So same equation, V equal KQ over R. I told we should include the sign of the charge, 8.99 10 to the power 9, which is K. Q is minus, so minus negative 15 10 to the power minus 6 over R is 0.10. Solve it, you will get the answer, that is negative 1.35 10 to the power 6 volt. Okay, so there could be a question with different geometrical shapes. It's a square ABCD is a square. The length of one side is 5 centimeter. So there are 2 point charges kept on the corners at A positive 12 microcoulomb and at point C negative 8 microcoulomb. The question is, what is the electric potential at point D? Okay, we know that electric potential is a scalar quantity. No direction, this is easier. Earlier I did for finding the resultant electric field strength. There we need to use Pythagoras theorem, everything I told that earlier. But potential is a scalar quantity. So the resultant potential at point D is equal to potential due to the charge at point A plus V1 plus V2 scalar quantity. So V1 is equal to K Q1 over R1 plus K Q2 over R2. Simply we can write, we need to include the sign of the charge. Okay, so that is 8.99 10 to the power 9. Q1 is 12 microcoulomb, so into 12 into 10 to the power minus 6 over the distance is 0.05 plus 8.99 10 to the power 9. Q2 is negative 8 minus 8, so minus 8 10 to the power minus 6 over 0.05. Solve it. It could be positive or negative. It's okay, whatever it is. So when we solve, we get 7.19 10 to the power 5 volt. That's a resultant electric potential at point D. Okay, so next thing you must know, what is the relationship between the electric potential at a point, the net or the resultant electric potential at a point, and the resultant electric field strength at the same point. What's the relationship? Okay, so you should know that is the resultant electric field strength at a point is equal to the potential gradient at the same point, E equal to minus dV over dx. Better know that. We won't get any questions related in the calculus format, but better know that the resultant electric field strength at a point is equal to negative potential gradient at that point. Better to know that. Okay, we know that the equation V equal KQR is applicable only for point charge, but we can use this for, as I used earlier for metal sphere. Here also I can use it for metal conductor or metal sphere or conducting sphere, when it carries a uniform distribution of charge on its surface. Here also we can use the same equation V equal KQ over R by assuming the whole charge is concentrated at the center. If the total charge on the surface, which has uniform distribution on its surface, if it is 10 microcoulomb, I can assume the whole charge is concentrated at the center. But you must know that for a metal conductor, I told this is not a hollow sphere, it's a solid sphere. So inside, at any point, the electric potential will be same, that is equal to the electric potential on its surface. Remember that in a metal conductor, the electric potential inside it at any point is equal to the electric potential on its surface. Why can't it have different potential inside? You know that if there is different potential inside the metal sphere, metal consists of delocalized electron, free electrons, so there will be current flow. If there is current flow, means the charge which distributed on the surface won't be a static charge. There will be current flow, means there is a flow of charge, so that never happens. Also we can say if the charge moves inside, there is current flow. If there is current flow, there is electrical energy. From nothing, no other work done, so it is not possible. Therefore, inside the metal sphere, all the points should have the same potential, that is equal to electric potential on the surface of the metal sphere. We can use this equation by assuming the whole charge is concentrated at the center. Also, we can explain why the electric potential inside the metal must be the same at all points. We already explained that inside the metal sphere, the electric field strength is equal to 0, and we know that E equal minus dV over dx. So electric field strength inside is 0, means the derivative or the potential gradient equal to 0, means the potential must be same. There is no difference in the potential inside the metal when we consider 2 points. That is differentiation of potential with respect to distance between two tiny close-up points must be equal to 0, means the potential must be the same inside it. Okay, so the total charge, uniform distribution of total charge on the surface of the metal sphere is 20 microcoulomb. The radius of the sphere is 8 centimeter. The center is O. First part question, find the potential at 5 centimeter from O. So I told that potential at 5 centimeter means it's inside the metal sphere. The potential at 5 centimeter is same as potential on its surface. So the equation V is equal to KQ over R. So 8.99 10 to the power 9. The total charge I can assume concentrate at the center. So 20 into 10 to the power minus 6 over. The question is at 5 centimeter, but I can't substitute 5 here because inside the metal sphere the potential is same as on its surface. So I should substitute 8 centimeter, that is 8 into 10 to the power minus 2 volt. So solve it, you will get the answer, that is equal to 2.25 10 to the power 6 volt. Okay, so the next question, find the electric potential at point B, which is at 4 centimeter from the surface. From the center it is at 12 centimeter. So the equation B equal to KQ over R. K 8.99 10 to the power 9. The total charge concentrated at the center, I can assume that way. So 20 into 10 to the power minus 6 over. The distance R from O is 12 centimeters. So 12 into 10 to the power minus 2. So solve it. You will get 1.50 10 to the power 6 volt. Okay, so we learned in unit 1 when a mass, a particle or ball or whatever it is that has mass, when it moves in gravitational field, it possesses both kinetic energy and gravitational potential energy. Same way, when a charged particle moves in electric field, it consists of both kinetic energy and electrical potential energy. Okay, so the electrical potential energy of a charge Q at point P. So imagine there in a space there is point P. The electric potential at that point is V. The electric potential at point P is V, and there's a charge Q is kept, or maybe a charge Q is passing the point P. So when the charge Q passing the point P, or when it is at point P where the electric potential V created by the electric field surrounding it, then the electrical potential energy of the charge Q, electrical potential energy of the charge Q is given by electric potential V into Q, electric potential at that point V into Q. Say for example, we'll imagine there's a charge Q kept in space at a point P at a distance R. The electric potential created by charge Q at point P is given by V equal KQ over R. Okay. At point P, there's a charge Q1 is kept. At point P, a charge Q1 is kept. What is the electrical potential energy of the charge Q1? So the charge Q1 is in the electric potential created by the point charge Q. So the electrical potential energy of charge Q1 is given by the electrical potential energy created by Q at point P. If I say that is V into Q1, but V is equal to KQ over R. KQ over R into Q1 is the electrical potential energy of point charge Q1 when it is in the electric field or electric potential created by another point charge capital Q. That also you must know. The electrical potential energy is given by electrical potential at a point into charge kept at that point, that is electrical potential energy of charge Q. So the V could be a uniform field, we'll come to that point, or maybe the potential V is due to a point charge Q. Then if it is stated by a point charge Q, then KQ over R into Q or Q1, that is electrical potential energy of charge Q1. You must know that. The unit of electrical potential energy is joules. Okay, so in unit 1 we learned that in gravitational field or work energy power in unit 1 we learned if I throw a ball vertically upwards, what happens when the ball moves upwards? It possesses both kinetic energy and gravitational potential energy. We say that loss in kinetic energy of the ball is equal to gain in gravitational potential energy of the ball when the ball moves upwards, when it is thrown vertically upwards. Same way, when we drop a ball, it will fall freely under gravity downwards. There we say loss in gravitational potential energy equal to gain in kinetic energy. Loss in GPE equal to gain in kinetic energy, we say. The same way, when a charged particle moves in electric field, there will be loss in kinetic energy equal gain in electrical potential energy, or loss in electrical potential energy equal to gain in kinetic energy. Either way, it could happen when it moves in electric field where there is no other friction or drag force. So, how to identify a charged particle is gaining or losing kinetic energy when it is moving in electric field? Better to know that. For example, first you must know that when a positive charged particle moves from a point with higher potential to point with lower potential. Carefully listen. When a positively charged particle moves from point with higher potential to point with lower potential, the positively charged particle will gain kinetic energy and lose electrical potential energy. Say for example, there are 2 points x and y in space. The potential at point x is V1, this is V2. A positive charged particle Q1 is moving from x to y. So there, if I say if V1 greater than V2, that is higher potential, lower potential, what will happen? The positive charge particle Q1 will gain kinetic energy and lose electrical potential energy. Same way, if it is a negatively charged particle, when a negatively charged particle moves from a point with lower potential to point with higher potential, negatively charged particle will gain kinetic energy and lose electrical potential energy. Negatively charged particle, when it moves from a point with lower potential to point with higher potential, the negatively charged particle will gain kinetic energy and lose electrical potential energy. Say for example, this is a negatively charged particle. So if I say V1 less than V2, V1, the point X has lower potential, point Y has higher potential, then the negatively charged particle, when it moves from X to Y, it will gain kinetic energy and it will lose electrical potential energy. We know potential could be positive or negative. So how to identify higher potential, lower potential? I'll consider two different numerical values, 5 and 2. So if there's a point that has 5 volt, there's another point that has 2 volt, means the point with 5 volt is higher potential, point with 2 volt is lower potential. We'll consider another 2 points. A point which has 5 volt, another point has negative 2 volt, means point that has 5 volt is higher potential, negative 2 or minus 2 volt is lower potential. Same way, there's another point, a point has minus 5 volt, another point has positive 2 volt, means the point that has minus 5 volt is a lower potential point and the point with 2 volt is a higher potential point. Same way, when we consider minus 5 volt, minus 2 volt, two different points. The point that has minus 5 volt is lower potential point. The point with minus 2 volt is higher potential point when we compare these two voltages. Okay, so there are 2 points X and Y with potential V1, V2. A charge Q is moving from X to Y. The work done in electric field when a charged particle moves from one point to another point is given by W equal Q times delta V. Delta V is the potential difference between the 2 points from where to where it is moving. Normally we can keep delta V always a positive quantity in terms of modulus watt value, no problem. We can use the signs also, but it might confuse. I did that way in my normal lesson, but for simple thing we can keep always the potential difference as a numerical value modulus positive quantity. Okay, I'll show some few examples. So first we'll say a charged particle, the Q is equal to 1.6 10 to the power minus 19 Coulomb, and V1 is equal to 2.5 volt, and V2 is equal to 4 volt. Okay, a charge, a positive charge is moving from point X which has 2.5 volt to point Y that has 4 volt. So we know that Q is a positive charge. It's moving from lower potential to higher potential. When a positive charge particle moves from lower potential to higher potential, what will happen? I already told that the charged particle will lose its kinetic energy and gain gravitational potential energy because it's a positively charged particle. So the work done in electric potential is given by 1.6 10 to the power minus 19 into delta V, 4 minus 2.5, that is equal to 1.5 joules. Solve it. You will get the work done, that is equal to 2.4. That is equal to 2.4 into 10 to the power minus 19. So this is the loss in kinetic energy. So loss in kinetic energy is equal to 2.4 10 to the power minus 19 joule, or we can say gain in electrical potential energy, that also 2.4 10 to the power minus 19 joules. Okay, when you consider this second example, the charged positive particle 1.6 10 minus 19 moving from a point with 4 volt to point with 2.5 volts, moving from X to Y. So here it's moving from higher point with higher potential to lower potential, means positive particle when it moves from higher potential to lower potential, it will gain kinetic energy. So gain in kinetic energy is equal to 2.4 10 to the power minus 19 joule, or loss in electrical potential energy is also the same. Okay, so here a positively charged particle 1.6 10 to the power minus 19 Coulomb is moving from higher potential 2.5 volt to lower potential which is minus 4 volt. So the delta V, when we consider the delta V is equal to minus 4 minus V2 minus V1. So the delta V means V2 minus V1. We can deal with the numerical value modulus. So minus 4 minus 2.5, that is going to be minus 6.5 volt. So when we consider the work done, that is Q into delta V, Q is 1.6 10 to the power minus 19 into minus 6.5. I don't want to include because there are another way we can approach. If the work done becomes negative quantity, we can say the particle is gaining kinetic energy. If the work done becomes positive quantity, we can say the particle is losing kinetic energy. But we don't need to go in that way. We can identify whether it's moving from higher potential to lower potential or lower potential to higher potential. So here I know a positively charged particle is moving from higher potential to lower potential. Lower potential minus 4. So it's going to gain kinetic energy. How much will it gain? Q into delta V. Delta V, I'll put it the numerical value, the modulus 6.5. So when you solve this, you will get that is equal to 1.04 10 to the power minus 18 joule. So that is gain in kinetic energy is equal to 1.04 10 to the power minus 18 joule, or loss in electrical potential energy, the same numerical value 1.04 10 to the power minus 18. Okay, so here a negatively charged particle minus 1.6 10 to the power minus 19 Coulomb. That particle is moving from X to Y, that is from V1 potential to V2 potential. V1 potential is minus 2.5 volt, V2 is minus 4. So minus 4 is lower than minus 2.5. That means a negatively charged particle is moving from point with higher potential to point with lower potential. So I told that when a negative charged particle moves from higher potential to lower potential, the negatively charged particle will lose its kinetic energy. So delta V, if you find V2 minus V1 minus 4 minus 2.5, so it's going to be minus 1.5 volt. I can keep plus 1.5 when I consider the work done. So work done is equal to Q into delta V 1.6 10 to the power minus 19 into delta V 1.5. So there, when you consider the work done becomes 2.4 10 to the power minus 19 joule. But since it's moving from a point with higher potential to point with lower potential, it's going to be losing kinetic energy. It's going to lose kinetic energy. That is equal to 2.4 10 to the power minus 19 joule. Okay, so it's an exam type question. 2-point charges, 3 positive 3 picocoulomb and positive 12 picocoulomb. They are kept 15 centimeter apart. On the line that joins the 2-point charges, there is a point P that is at a distance of 5 centimeter from positive 3 picocoulomb. The question is, first part, find the electric potential at point P. So it's a scalar quantity. The potential at P is given by V1, V2, where V1 is the potential of 3 picocoulomb at P. V2 is the electric potential of 12 picocoulomb at P. So just substitute and solve it. It's simple. So that is K Q1 over R1 plus K Q2 over R2. So 8.99 10 to the power 9. Q1, that is 3 pico 10 to the power minus 12 over R1 5 centimeter 0.05 plus again 8.99 10 to the power 9. Q2 12 picocoulomb, 12 into 10 to the power minus 12 over, pico means 10 to the power minus 12. R2, the distance of P from here, this is 15, this is 5, means that is 10 centimeter 0.10. So solve it, you will get 1.62 volt. That's the electric potential at point P. Okay, the second part question. A silver nucleus which has mass number 107, atomic number or proton number 47 has speed u when it is a long distance from P. Long distance from P means the electric potential of these two point charges at the point where the silver nucleus was there initially is equal to 0. That means when the silver nucleus is at the initial point, it won't have any electrical potential due to these 2 point charges because it's far distance. You know that when the R becomes much larger, the potential will become 0. So negligible potential due to the 2 point charges at the initial point of silver nucleus. The question is, calculate the minimum value of speed u such that the nucleus can reach P. So you know that the nucleus is a positively charged particle. Initially, at the point where the silver nucleus was there, the electric potential is 0, far distance from these two point charges. So it's moving from a 0 potential to a point P that has potential of 1.62 volt. That means a positively charged particle, that is the silver nucleus, is moving from lower potential to higher potential. I told that whenever a positive particle moves from lower potential to higher potential, it will lose its kinetic energy. The question is, find the minimum value of speed u when it is at the initial point. From there, it's moving towards point P. So minimum value means we assume it's able to reach the point P, but when it touches the point P, it lost all its kinetic energy and the kinetic energy become equal to 0. That's the idea. Minimum kinetic energy, minimum speed at far distance where the speed is u, they ask to find the minimum speed. So that means at initial point, if I take the point is n, from n to P when it moves, it's moving from point with lower potential to higher potential, the silver nucleus is going to lose kinetic energy. So minimum value of initial kinetic energy such that it reaches the P means when it reaches the P, its kinetic energy becomes equal to 0. So simple. We know the electric potential at P. We already found it in the first one, which is 1.62 volt. Okay, we'll answer like this. So for the silver nucleus, we can say loss in kinetic energy because positively charged silver nucleus is moving from lower potential, that is far distance 0 volt, to higher potential 1.62. So it's going to lose its kinetic energy. Loss in kinetic energy is equal to we can say gain in electrical potential energy. Gain in electrical potential energy is equal to Q into delta V, or work done against electric potential. Either way we can say. So the answer, loss in kinetic energy equal gain in electrical potential energy or work done against electric potential. Either way we can say. Or work done against electric field. Anyway, we can say, for example, when I throw a ball, when it moves up, it's gaining gravitational potential energy equal to loss in kinetic energy. Or we can say loss in kinetic energy equal to work done against work done against gravitational force. Either way we can say. Here also we can say work done against electrostatic force or work done against electric potential or gain in electrical potential energy. Either way we can say whatever it is, Q into delta V. So loss in kinetic energy initially half m u squared minus half m v squared is equal to Q times delta V. Okay, so we'll substitute it. So mass of the gold nucleus we can find 107. That's the total nucleons. Mass of the proton is almost equal to mass of the neutron. The mass of the gold nucleus is not given, we can calculate it. We know mass of proton is almost equal to mass of neutron. Mass of proton given in the data sheet 1.66 10 to the power minus 27 kilogram. So half into the mass is 107 into 1.66 10 to the power minus 27 kilogram. That's a mass of the silver nucleus into u squared equal, minus 0, because we assume the minimum initial kinetic energy, minimum speed such that it reached the point P, means when it reaches the point P, the speed becomes 0. So final kinetic energy 0 is equal to, charge is, there are 47 protons, so 47, charge of 1 proton 1.6, 10 to the power minus 19, delta V, the potential difference. Initially at far distance potential equals 0. At point P we found the potential, that is 1.62, so 1.62 minus 0. Okay, solve it and find the U, that's all. You will get U is equal to 1.17 10 to the power 4 meter per second. Okay, so this question based on Rutherford alpha particle scattering experiment, or it's nothing, any wherever a positive particle approaches another positive particle, we can have a same type of question. It appeared in the past paper. So in this question, alpha particle, you know alpha particle is the helium nucleus, its charge is plus 2 times 1.6 10 to the minus 19 Coulomb, and its mass is equal to 4 times the mass of proton, so it's not an issue. So their alpha particle is moving at a speed of 1.5 10 to the power 7 meter per second. At far distance from the gold nucleus, it's moving towards the gold nucleus. So when the alpha particle moves towards the gold nucleus, it's a positively charged particle. Gold nucleus also positively charged particle. So the gold nucleus is at a fixed point, it won't change its position. So the alpha particle will experience repulsive force, so it will slow down. Finally, it will come to rest somewhere at point P. Or we can say the alpha particle has initially kinetic energy. It's positively charged particle. It's moving from a far distance point where the electric potential of the gold nucleus at the initial point of the alpha particle is equal to 0. But at point P where there is a positive electric potential created by the gold nucleus, so alpha particle is moving from a lower potential which is 0 to higher potential. So lower potential to higher potential, a positively charged alpha particle is moving, so it's going to lose kinetic energy. So the question is, what could be the closest approach, closest distance reached by alpha particle from the gold nucleus? I need to find the distance x. Okay, so we know initially the alpha particle is at far distance where the electric potential of gold nucleus, which consists of 79 protons. So the charge of gold nucleus 79 into 1.6 10 to the power minus 19 Coulomb. So the electric potential of gold nucleus at the initial point of the alpha particle is 0 because alpha is initially at far distance. Okay, so there we can say like this, the alpha particle when it moves from initial point to point P, it's losing the kinetic energy and gaining electrical potential energy, or doing work against electric field. Okay, so there we can do like this, loss in kinetic energy equal work done against electric field or gain in electrical potential energy for alpha particle. I'm writing for alpha particle. Loss in kinetic energy, initial velocity half times mass of the alpha particle. I told it consists of 2 protons, 2 neutrons, mass of proton given in the data sheet. So 4 times 1.66 10 to the power minus 27 kilogram. Initial speed is given 1.50 10 to the power 7 all things squared minus final kinetic energy where it reaches the closest point. It has lost all its kinetic energy because closest point is unable to move further beyond it. So there the speed 0, kinetic energy is 0. Gaining electrical potential Q into delta V. Q into delta V. The charge of the alpha particle is He2 plus. So 2 into 1.6 10 to the power minus 19 into the potential difference. Initially the potential, when it is at the far distance, potential is 0. At point P, the potential, let it be V. That potential is due to the gold nucleus. Okay, from this, find the potential at point P. I can say Vp, the potential at point P, minus 0 initially when it is at far distance. The potential of the alpha particle at that point is 0 because it's at far distance from the gold nucleus. When the distance becomes much larger, r becomes much larger, potential will become equal to 0. Okay, so find the potential that is equal to Vp will be equal to 2.33 10 to the power 6 volt, that is created by the gold nucleus. Okay, so we know that that is created by the gold nucleus. So that is equal to Vp is equal to kq over r. K, q is the charge of the gold nucleus, over r, that is x. So I need to find the x. So k, that is 8.99 10 to the power 9. Charge is 79 protons, 79 into 1.6 10 to the power minus 19. Okay, divided by x, that is equal to Vp. Vp is equal to 2.33 10 to the power 6. Okay, solve. X will be equal to, from this, x will be equal to 4.87 10 to the power minus 14 meter. That is the closest distance alpha particle reached from the gold nucleus. Okay, so this also exam type question. A and B are two identical solid metal spheres. I am not writing the question, so I'll read it. A and B are two identical solid metal spheres. They carry different amount of charges. A and B, they are carrying different amount of charges on its surface. The charges are uniformly distributed on their surface. The P is a point at a distance x from the center of the sphere A. The distance between the two centers is 20 centimeters. They have the same radius. They are identical spheres, but only different. They are carrying different magnitude of charges. Okay, so P is a point at a distance x from the center of the sphere. So the graph shows how the electrical potential created by the two the charge distribution on the spheres varies when the P moves from 0 to, that is from center of the sphere A to center of the sphere B. When P moves, that means x becomes 0 to 20, how the potential varies, that is given by a graph potential versus x in centimeter, potential that is in volt. X is measured from center O1 to center O2 of the two spheres. They have same radius but different magnitude of charge they are carrying. Okay, first part of the question, I am not writing it, I will give the explanation. State and explain whether two spheres have charges of the same or opposite sign. So the question is, first part, nothing is mentioned about the charges, but they are carrying different magnitude of uniform distribution of charge mentioned in the question. So the question is, are they carrying positive charges or positive and negative or negative charges? That's the question they ask. So the answer, when you consider the potential graph at any point from O1 to O2, the potential is shown on positive side. Therefore, both spheres are carrying positive charges. On the graph, the potential is always on the positive side, so they are carrying, both are carrying positive charges. That's the answer for the first part. Second part, state the radius of the spheres. Okay, I told that when we consider potential of a metal sphere when it carries uniform distribution of charge, I told they will have the same potential everywhere inside the metal, which is equal to potential on the surface. So here you can see the potential is remaining constant until the x becomes 1.5 centimeter. Again, from 18.5 to 20, 20 is the distance from center to center. So 18.5 to 20, again the potential is same. So this is the radius of the sphere where the potential is same. Here also 20 minus 18.5, that also radius. So the second part, they asked to state the radius. So radius is equal to 1.5 centimeter. Both are identical spheres, both have the same radius, 1.5 centimeter. How do we determine that? The potential is constant everywhere inside the metal sphere from the center to surface. Okay, third part. State the distance of null point at a state the distance of the null point from the center of the sphere A. The third part, state the distance of the null point from the center of the sphere. Okay, how are you going to find the null point? Null point is the point at which the electric field strength or resultant electric field strength is equal to 0. And also we know that electric field strength is given by potential gradient, negative potential gradient. So that means if I draw a tangent at any point, that will give the electric field strength at that point. If I draw a tangent at this point, if I find the gradient of the tangent, that will be equal to electric field strength at that point. So electric null point means where the electric potential equal to 0 means when I draw a tangent, the gradient must be equal to 0. Where will be the gradient 0? Only at this point, because here the gradient 0, yes, we know inside the metal sphere we don't say null point, because other than the electric field inside the metal spheres, outside the metal sphere, where will be the null point? It is at this point where 11 centimeter from the center O. If I draw a tangent here, there the gradient of the tangent will be 0 because it's a lower point. The tangent will be like this, which has 0 gradient. So other than metal, inside the metal, we know electric field is 0, but we don't say null point, that one. But outside the metal point, where will be the null point? At a distance of 11 centimeter from O. How do I know? The tangent will be horizontal at 11 centimeter. So the null point at 11 centimeter from O1, center of the O. Next part, find the charge on the metal sphere A. Fourth part, find the charge distribution or the total amount of charge on the metal sphere A. So that's nothing, we can use V equal KQ over R. So we know the electric potential on the surface, which is 0.76, V equal KQ over R. On the surface electric potential 0.76 equal 8.99. 10 to the power 9. I need to find the Q1, the charge on the metal surface A, over R, the radius, that is 1.5 centimeters. So 1.5 into 10 to the power minus 2. Find the Q1. That will be equal to 1.268 10 to the power minus 12 Coulomb. Okay, next part, find the charge on the sphere B. Same method, same approach. So I'll do it here. The fifth part, find the charge on sphere B. Same way, the potential at which is 0.54. So use the same equation, V equal K Q2 over R. So that is 0.54 equal 8.99 10 to the power 9. The charge Q2 I need to find over R, the radius of the sphere, also 1.5 10 to the power minus 2. So Q2 will be equal to 9.01 10 to the power minus 13 Coulomb. Check the answers are correct. Yeah. Okay, sixth part. Find the electric potential at point 11 centimeter from the point A, center of the center of the sphere A. Okay, so that is given as V naught on the graph. We need to find the value of V naught. So we know the charges of sphere A and sphere B. So the potential at point at 11 centimeters. So V is equal to V1 plus V2. V1, V2 are the electric potential created by the charge on sphere A and charge on sphere B. So K Q1 over R1 plus K Q2 over R2, that is V naught. We need to find the V naught, which is marked on the graph, which is at 11 centimeter. So that is 8.9 K. I can take commonly, or I can write twice. 8.99 10 to the power 9. Q1, the charge of first sphere, we found it, that is 1.268 10 to the power minus 12, 1.268 10 to the power minus 12 Coulomb over distance is 11 centimeters, 0.11 plus 8.99 10 to the power 9. Q2 we found it as 9.01 10 to the power minus 13 divided by the distance from center of the second sphere. So from the first sphere the distance is 11 centimeter, means the total distance 20. So 20 minus 11, 9 centimeter, 0.09. Solve it, you will get the V naught. That will be equal to 0.19 volt. Okay, so the last part of this question, an alpha particle is initially at rest on the surface of sphere A. Alpha particle, you know, it's a positively charged particle. It's at rest on the surface of A. The alpha particle moves along the line joining the two centers of the sphere. So alpha particle is initially at maybe at this point at rest. It's moving along this line from this point to this point on the same line that's connecting O1, O2. Along that line, the alpha particle is moving from rest from A, sphere A to sphere B. Find the maximum speed of the alpha particle during its motion. That's the question. Find the maximum speed. Okay. Now look at here. Carefully think and answer. So alpha particle is initially on the surface of sphere A, where the electric potential of sphere A is 0.76 volt. On the surface of sphere B, the electric potential is 0.5 volt, which is lower than the potential of the sphere A, right? Alpha particle is a positively charged particle. So it's moving from, a positively charged particle is moving from higher potential to lower potential. I told that whenever a positive particle moves from higher potential to lower potential, it will gain kinetic energy, so its speed will increase. But the question is, find the maximum speed. So maximum speed means we can say gaining kinetic energy equal work done against electric potential, or gaining kinetic energy equal to losing electrical potential energy, whatever it is, that is equal to Q times delta V. Okay, gaining kinetic energy half mv squared minus half mu squared equal Q times delta V. U initially at rest, they are saying alpha particle is released from rest from the surface of sphere A. So U is equal to 0. So the final speed half mv squared equal to Q delta V. Right, now look at here. The question is, find the maximum final speed. So when V wants to be maximum, Q charge of the alpha particle is 2 into 1.6 10 to the minus 19. There is no change. So if I want to have the maximum final speed, delta V should be the maximum. delta V should be the maximum compared to from the initial potential, which is 0.7 means 76 means I need a maximum difference, means that happens at 11 centimeter, because that is the point with lowest potential. So when I consider this point and this point, the potential difference will be 0.76. V naught, we found it as 0.19. That could be the maximum. So half mv max squared equal to delta V, the potential difference, delta V maximum. Okay, so that happens when 0.76 minus V naught. V naught is the lowest point with potential 11 centimeter from the center of O. Okay, so now we can find half into mass of alpha. It consists of 4 nucleons. So 4 into 1.66, 10 to the power minus 27 into V max square. Charge of alpha plus 2, 2 into 1.6 into 10 to the power minus 19. V max, that is 0.76 minus 0. At V naught, we found V naught as 0.19. So that will give the maximum difference. Okay, solve it, V max. So that will be 7,410 meter per second. Okay, so the application of work done by electric potential gain in kinetic energy is electron gun. That is, the electron guns are used in cathode ray oscilloscope, the old model computer or television monitors. Even in X-ray machines, electrons are accelerated after they emitted. They will be accelerated by the electric potential, and the electrons will gain kinetic energy and they hit the tungsten and X-ray will be emitted. Even in fluorescent lamp tube lights, electrons are emitted, and when they pass through the mercury vapor, they hit the electrons of the mercury atoms, they de-excited the UV radiation emitted. Then when the UV photons are absorbed by the fluorescent phosphorus, it emits the light. So like that, the electron gun is used in different applications. So basic thing here, there's a heater. This is a heater which consists of a low voltage. So this is cathode, this is anode. Cathode and anode, they looks like just like a rods, but actually cathode and anode are like circular discs. Anode is consisting of a hole at the center like a compact disc. So it looks like in 2-dimension broken disc, broken stick, but actually it's like this. Okay, so the electron will be emitted from the cathode due to thermionic emission. Thermionic emission means when a metal is heated, the atoms will absorb the heat, and the atoms of the metal absorb the heat and they will vibrate. Due to the vibration, electrons will be released. That process is called thermionic emission. So the electrons will be emitted from the cathode. A high voltage is applied across cathode and anode. So this will become positive terminal, this will become negative terminal. So electrons will be attracted towards the positive terminal. So electrons are negatively charged particles. They are moving from low potential because that is negative potential, this is positive potential. Electrons are moving from low potential to high potential, so they will gain kinetic energy, as I explained earlier. So there we can use gaining kinetic energy of the electron equal work done by electric potential, or we can say loss in electrical potential energy, work done by electric potential, or loss in electrical potential energy. So that is half mv squared minus half mu squared equal q times delta v. Delta v is the potential between cathode and anode. Normally that is the high voltage, around 2500 volt. So mass of the electron we know initial speed mostly we take 0. So we can calculate the final speed when it reaches or when it passes through the hole or gap in the anode. We know the charge of electron, we know the potential difference applied across anode and cathode through which the electron is being accelerated. Normally 2500, 3000 volt. We know the mass of electron. Initial speed normally we take 0. So we can calculate the final speed. Okay, so far all the questions we came across related to radial field. Radial field means where the strength of the field will be different at different points, and when the distance increases from the charge, the strength of the field, that is electric field strength, will decrease. But uniform electric field means the strength of the field is the same at all point everywhere. Practically, where can we obtain, how can we obtain uniform electric field? Uniform electric field could be obtained in the region between oppositely charged parallel plates. So for example, there are parallel plates, parallel metal plates. This is positively charged, and this consists of same magnitude of negative charge, that is opposite side. So 1, 2, 3, 4, 5, 6, 7. So same magnitude of charges but opposite side. So the electric field in the, actually this looks like rod. No, they are not rods. They are oppositely charged parallel plates. If I draw in 2 dimension, it will be something like this. Oppositely charged parallel plates. So this is a positively charged plate. This is a negatively charged plate, same magnitude of charge. Okay, so there in the region between the two plates, there will be uniform electric field. The field strength will be the same at all points. Why is it? So that means the uniform electric field means the field lines will be parallel with equal space. We should show. The electric field line, wherever you consider, will be directed towards the negative plate. Wherever you consider, the direction of the electric field will be vertically towards the parallel plate. That means vertically towards the negative plate. That means the field lines will be perpendicular to the negative plate as well as perpendicular to the positive plate. So field lines are perpendicular to the both plates. Why is it like that? We can explain like this. Imagine I am keeping a positive test charge here in 3 dimension. So this is identical charges. So I should draw exactly the same way. But yeah, both have the same magnitude of charge. Imagine a test charge is kept in the region between the positive plates. Imagine in 3 dimension. So on the positive test charge, all the charges will exert symmetrically the electrostatic force. For example, if this charge exerted electrostatic force this direction, symmetrically this charge also will exert same magnitude of electrostatic force. If this charge exerts electrostatic force this way, then this charge will exert electrostatic force this way. So like that in 3 dimension, when you consider the electrostatic force acting on the positive test charge will be like a cone. If you imagine this is the positive test charge, the forces acting on the test charge, if you think about 3 dimension, it will be in a cone like this way. Every force has opposite direction, equal magnitude of force. So when you resolve all these forces into horizontal plane, they will cancel with the opposite direction of force. I think you can imagine this force, if I resolve it horizontally, that will be cancelled by this force. If I resolve this one horizontally, that will be cancelled by this force due to the symmetrical nature. So finally, the vertical component of the force will remain. All the horizontal component of force will be cancelled with the opposite force by the opposite force created by the other charge. So all the horizontal forces are cancelled. So finally, it will have only the vertical force as the net force. So the resultant force is vertically down. Therefore, the electric field lines are vertically down. We know that the direction of the resultant force acting on a test charge indicates the direction of the electric field. So wherever you keep this, it will have the resultant force vertically towards the negative plate such that the force is perpendicular to the plate. So in uniform electric field, the field lines are always from positive plate to negative plate such that the field lines are aligned perpendicular to the both plates. Normally, I told that the number of lines per unit area indicates the strength of the field. So, electric field strength is the same at all points. So, the field lines should be drawn parallel with equal space. Okay, we know that the electric field strength is the same at all points. So, what could be the electric field strength in the region between the parallel plates, oppositely charged parallel plates? At any point, there will be the same magnitude of electric field strength. So there are two opposite type of charger plates with charge. So there will be a potential difference across the parallel plates. If I say that is V, the potential difference between the parallel plates is equal to V, and the distance between the parallel plates is D. The potential gradient, again I am going to use, but I am not going to derive it. The potential gradient is equal to potential difference, where V is the potential difference between the plates, not the potential. Careful. In this equation, V indicates the potential at a point at distance R from the point charge. Careful, students make mistake. Where V is the potential at a point at a distance R from the point charge V. But here E equal V over D, I am going to use the electric field strength E equal V over D, where V is the potential difference between the plates, not the potential, it's a potential difference between the plates, that is V. So that is the dV over dx, dV over dx, the potential gradient. We know that electric field strength, there's a negative sign, we don't need to consider that. So I already told that potential gradient is the electric field strength. So potential difference, dV means potential difference between 2 points, dx is the distance between those 2 points that has potential difference dV. That's a meaning in calculus. So the distance between the 2 points is V, the distance between the two parallel plates is D, and the potential difference between the two plates is V. So the electric field strength equal V over D. It's a uniform electric field. So everywhere the field strength is the same. So if I consider 2 points in the region between the parallel plates, if the 2 points are at a distance of x, which is not equal to D, then the potential difference between these 2 points P and Q is given by that also the same electric field strength, that is the potential difference between points P and Q, it could be V1, the distance between them is x, that will be equal to V over D. Like that I can say some other points between here, these two, the distance is x1, the potential difference is V2. So there I can say equal to V2 over x2, like that. I can calculate the potential difference between any 2 points in the region between the parallel plates, because it's the same electric field strength. Okay, so we know that the unit of electric field strength according to the definition E equal F/Q, the unit of electric field strength is Newton per Coulomb. But in this equation, the unit of the electric field strength becomes volt per meter. Unit of electric field strength becomes volt, because the voltage is divided by the distance, which is in meters. So volt per meter. So are they same? Volt per meter and Newton per Coulomb, are they same? They can ask. Okay, I'll show they are same. So the unit of E, electric field strength, according to this, volt per meter. I'm going to get Newton per Coulomb from volt per meter. Volt means joule per Coulomb times per meter. Joule means Newton meter, you know, work done, W equal F into D. Joule means Newton meter into per Coulomb into per meter. So meter per meter get cancelled, Newton per Coulomb. So I'm getting the unit as here, starting from volt per meter, I'm getting this one. So both are the same identical units. Okay, so I wrote E equal V over D. This equation is could be used only for uniform electric field. For radial field, we use all these equations. But this equation could be used any type of field. For example, when a charge Q is kept in a field, it could be a uniform field or non-uniform radial field. Where the electric field strength is E, we can find the electrostatic force acting on the charge Q by using F equal QE. But where Q must be a point charge. Careful again. In these equations, V is the potential. Uh, this is also potential, but here delta V is the potential difference between 2 points in radial field when we consider the work done. But in uniform electric field, V is the potential difference between 2 points and D is the distance between the two relevant points. The potential difference between the 2 points that are at those are at distance D apart is V potential difference. Okay, so that's the equation for uniform electric field. Okay, so there could be a question like this related to uniform electric field. Uh, Parallel plates consist of same magnitude of opposite sign of charges. The potential difference between the parallel plates is 9 volt. The distance between the parallel plates is 5 centimeter. An electron is released from rest from the negative plate. Find the speed of the electron when it just reaches the positive plate. That could be a question. Okay, this could be done in two different ways. Now, we can't use equations of motion in radial field because in radial field, the force will be different at different points because the field strength is different. So, if the field strength is different, force acting on the charged particle will be different at different points. So, if the force difference means according to F equal ma, the acceleration of the particle won't be the same when a charged particle moves in radial field. For example, if there is a positively charged particle or nucleus, a gold nucleus is there. So if we release an alpha particle from rest here, the gold nucleus is positively charged particle. Alpha particle also positively charged particle. So due to repulsive force, alpha particle will move away from the gold nucleus. But the acceleration of the alpha particle won't be constant because when the alpha particles moves away from the gold nucleus, the electric field strength will decrease according to equal kq over r square. So the electrostatic force acting on the alpha particle also will decrease according to F equal QE. So F equal ma, the acceleration of the alpha particle will be different at different points. It won't be constant. So we can't use equations of motion. But in uniform electric field, the electric field strength is the same. Wherever the electron stays during its motion, it will experience the same electric field strength and it will have the same electrostatic force. So same electrostatic force means according to F equal ma, it will have the same acceleration. It's going to move on a straight line from here to here along the field lines towards the positive plate. So there we can use equations of motion. We can't use equation of motion in radial field. Okay, so first method I'm going to use it's a long step, doesn't matter. I'm going to use equations of motion. So I'm going to find the force acting on the electron. We know the charge of electron 1.6 10 to the power minus 19 Coulomb, mass given in the data sheet 9.11, 10 to the power minus 31 kilogram. The question is find the speed of the electron. It's released from rest. Initially it's at rest. From rest it's released moving towards the positive plate. So the speed near the positive plate or closer to the positive plate we need to calculate. Okay, so we can use the electric field strength E equal V over D. So the potential difference 9, D must be in meters, so 0.05. So the electric field strength between the parallel plates will be equal to 180 Newton per Coulomb or volt per meter, anything I can use, I already showed it. So the force acting on the electron F equal QE, the electrostatic force. So F equal QE, the charge of the electron 1.6 10 to the power minus 19. Electric field strength 180. So the force, the electrostatic force acting on the electron is Well, I didn't find it. If you want, you can find that. Okay, so that is 2.88 10 to the power minus 17 Newton. Okay, so during its motion, what's the resultant force? Do we need to consider the weight of it? No, we don't need to consider the weight, because the weight of, normally we don't consider the weight of the particles when they move, like in electric field. For example, weight of, like this, weight of electron, weight of proton, weight of alpha particle, weight of any nucleus we don't consider during questions like this, because the weight is much smaller compared to the electrostatic force exerted on it. So if you want, you can consider, but it's an unwanted thing. There won't be any change. You know, mass of electron 9.11 10 to the minus 31. If you multiply by 9.81, compare that weight with this uh, electrostatic force, it's much smaller. So don't consider the weight of the electron. So the resultant force is only due to the electrostatic force. So now I can use F equal ma for the electron. The electrostatic force is the resultant force. We don't consider the weight. So 2.88 10 to the power minus 17 equal mass of electron given in the data sheet 9 into A. Find the acceleration. So the acceleration of the electron will be 3.16 10 to the power 13 meter per second squared. Okay, now I can use towards the positive plate for the electron v squared equal u squared plus 2as, because constant acceleration. I need to find the v. So initial speed is 0, released from rest 2 times. Acceleration is 3.16 10 to the power 13 into the distance is going to move 5 centimeter. 5 into 10 to the power minus 2. Take the v, that's the final speed. So that will be equal to 1.78 10 to the power 6 meter per second. That's the speed when it just reaches the positive plate. Okay, so this is little longer step. I can use the same method what we used here. Find the potential difference. W equal QV, gain in kinetic energy equal work done against electric potential. We can get it in 2 or 3 lines. I'll do it as a second method now. Okay, so method 2, we can say gain in kinetic energy of the electron equal work done by the electric potential, or loss in electric potential energy. Either way, we can say work done by electric field. So gain in kinetic energy, half m v squared minus half m u squared equal charge of the electron q into delta v, the potential difference between the two plates, or potential difference between the initial point of the electron and the final point, which is positive plate. So mass of electron given 9.11 10 to the power minus 31 v squared. Initially it was at rest. 1.6 10 to the power minus 19. Delta v, potential difference, that is 9. Find the v, you will get exactly the same answer what we got earlier. 1.78 10 to the power 6 meter per second. So this shorter steps, that is longer, but anyway both are correct methods. Okay, so there could be a question like this. When you connect a power supply, DC power supply to parallel plates, the voltage across the parallel plates will become same as the EMF of the power supply. The plate which is connected to the positive terminal will become positively charged, and the plate which is connected to the negative terminal of the power supply will become negatively charged. So you must know that. So the voltage across the parallel plates is equal to 12 volt. They are 4 centimeter apart. A charged oil drop is at rest or floating in the region between the parallel plates. So normally they ask what could be the type of charge the oil drop is carrying. So here we must consider the weight of the oil drop, because if we don't consider the weight of the oil drop, then if the only force acting on it is the electrostatic force, the oil drop will move along the direction of the electrostatic force. So here we should consider the mass of the oil drop or weight of the oil drop. But for the motion of charged particles like electron, proton, alpha particle, nuclei, any type of nuclei, we don't consider the weight because compared to the electrostatic force, the weight is negligible. But here this is an oil drop, so the mass is reasonably much larger compared to mass of alpha particle or mass of any nucleus. The mass of the oil drop is much larger, so it will have significant gravitational effect on it. Okay, so the since it's floating, we know the plates are kept in parallel, so they are two parallel plates. If I draw the free body force diagram for the oil drop, there are two forces. Anyway, the weight will act vertically down. So to balance it, the electrostatic force should act vertically upwards. It should balance the weight, is it? So there, the electrostatic force should be upwards, means it should be towards the positive plate, away from the negative plate, means the oil drop should carry negative charges. The oil drop must carry negative charge because then only it will experience electrostatic force towards the positive plate, away from the negative plate. So the electrostatic force is due to negative charge of the oil drop. So here the mass of the oil drop is given as 0.05. Mass of the oil drop is 0.05 into 10 to the power minus 6 kilogram. 0.05 10 to the power minus 6 kilogram. So the question is, find the charge of the oil drop. Okay, so we know it's at rest, means Fe must be equal to mg, the electrostatic force equal to weight of it. Electrostatic force Fe is equal to QE. I told you can use this equation anywhere. So here we take the oil drop as a point charge. It's in an electric field of E in the region between the parallel plates. So the electrostatic force acting on the oil drop, which is considered as a point charge, is equal to F. So Fe is equal to QE, where Q is the charge of the oil drop, E is the electric field strength in the region between the parallel plates, is equal to mg. We know that E equal V over D, so V over D is equal to mg. We need to find the Q, so Q is equal to cross multiply mgd over V. Substitute. Mass we know 0.05 10 to the power minus 6 kilograms. G is 9.81. D is the distance between the parallel plates, 4 centimeters, 0.04 over the potential difference, 12. So solve it. You will get the answer. That will be equal to 1.635, 1.64 10 to the power minus 9 Coulomb, or I can say 1.64 nanocoulomb, which is negative, is a negative charge. Negative charge. Okay, so this type of question appeared several times in the past paper. So oppositely charged parallel plates are kept 6 centimeter apart, and the potential or the voltage across, or potential difference across the plates, is 16 volt. An electron is moving parallel to the plates along the mid region, of the parallel plate. So that means the mid region means the path of the electron is at a distance of 3 centimeters from the plate CD and 3 centimeters from the plate AB. So the electron is moving along the mid region of the parallel plates. And the question is, will the electron hit the plate? So this length also given, I forgot to draw it. So the length of the plate CD and AB is given as 12 centimeter. The question is, we know that when the electron enters into the region between the parallel plates, the electron, here we don't need to consider the weight of the electron, negligible. So when the electron enters into the region between the parallel plates, it will experience electrostatic force upwards towards the positive plate, because electron is a negatively charged particle. So the electron will experience electrostatic force vertically upwards, means its horizontal component or the initial velocity parallel to the plates will remain unchanged because the electric field lines are vertically down from positive plate to negative plate. They exert electrostatic force on the electron vertically upwards towards the positive plate. There is no component of electric field parallel to the direction of initial velocity. So along the initial direction of velocity or along the line parallel to the plane of the plates, there is no electric field, so the velocity remains constant. No acceleration in horizontal direction. Not good to say horizontal direction, it's better to say there is no acceleration parallel to the plane of the plates. No acceleration, there is acceleration only in perpendicular to the plane of the plates towards the positive plate because it's a negative charge. Okay, so the question is, will the electron hit the plate AB? That's the question. Will the electron hit the plate AB? By using proper calculation, explain your answer. Nothing to explain, we need to consider the calculation. Okay, so we'll see the idea. How long will it take to move along or parallel to the plates a distance of 12 centimeter? Because if the electron has moved in the region between the parallel plates a distance of 12 centimeters parallel to the plane of the plates, then the electron won't hit the plate. So we will find how long will it take to travel parallel to the plates a distance of 12 centimeter because length of the plate is 12 centimeter. So we'll find the time taken for that motion. So there is no electric field parallel to the plane of the plate, so there is no acceleration. So we'll use S equal ut plus half at squared parallel to the plane of the plates, parallel to the plane of the plate. So in this diagram it is in horizontal direction because plates are kept in horizontal plane. So S 0.12, initial speed is the same as 5 into 10 to the power 6 meter per second into t. Horizontally, there is no electric field because electric field lines are perpendicular to the plate. So parallel to the plate, no component, so no acceleration. So find the time t. So the time taken to move 12 centimeter, that will be equal to 2.4 10 to the power minus 8 seconds. Okay, now we'll find what would be the acceleration of the electron because it's like a projectile motion what we learned in unit 1, but there the acceleration is we know 9.81, but here we need to find the acceleration. There when a ball is thrown horizontally, the ball will experience acceleration vertically down 9.81. So here vertically upwards, that means better to say rather than saying vertically upwards, perpendicular to the plane of the parallel plates in this direction, we need to find the acceleration. So the force acting on the electron in this direction, F, that's a resultant force, is the only electrostatic force, the weight is negligible. F equal charge of the electron into E, we know E equal V over D. So charge of the electron 1.6, 10 to the power minus 19 into V over D. The potential difference is 16 divided by distance 0.06. That is the resultant force acting on the electron. That is equal to MA. That is equal to MA, the acceleration of the electron. We can find mass is 9.11, 10 to the power minus 31 kilogram. Okay, find the acceleration. So acceleration is going to be 4.69 into 10 to the power 13 meter per second squared towards the positive plate. Okay, so we'll find during this time what distance will it move. So when it travels 2.4 horizontally 12 meters, the time taken is 2.4 10 to the power minus 8 seconds. So during this time, if the distance it could move is more than 3, that means it will hit the plate before it moves horizontally or parallel to the plate 12 centimeter. So we'll find what distance could it move when during this time. So vertically upwards we'll use S equal ut plus half at squared. So the distance it could move in upward direction. Initial speed parallel to the plates, we are using perpendicular to the plates, so no component of initial speed velocity, that is 0, plus half into acceleration 4.69 10 to the power 13 into the time we know 2.4 10 to the power minus 8 squared. So we will get that distance it will move is 0.0135 meters, that is 1.35 centimeter, which is less than 3 centimeter. That means when it completes parallel to the plate 12 centimeter, its vertical displacement is just 1.35 centimeter. So it will move out of the plate without hitting the plate AB. Because if this value becomes more than 3, that means when the electron completes 12 centimeter in this direction parallel to the plate, it has gone a distance more than 3, means it has already hit the plate. So here you should give the conclusion, the electron will move out of the plate without hitting the plate. Okay, the last point is equipotential surface. Equipotential surface means surface that passes through points with the same potential is called equipotential surface. So in equipotential surface, the work done is equal to 0 because same potential delta V will be equal to 0. So what could be the shape of equipotential surfaces? For example, if it is a point charge, positive point charge, so the distance same, V equal KQR, at same distance in 3 dimension, if you think there will be a sphere that will have the same potential. So the shape of the equipotential surface around a point charges will be spherical shape. The electric field lines are radial. Electric field lines will be perpendicular to the equipotential surface. So if I draw the electric field equipotential surface for a point charges, they will be spherical shape around it. There could be many different equipotential surfaces around it. Different equipotential surfaces will have different potential, but on an equipotential surface, all points will have the same potential. Now when we consider the work done W equal Q delta V, if we are moving a charge Q from one equipotential surface to another point of the same equipotential surface, delta V is 0, so the work done equals 0. Work done equals 0 means the charge neither gains nor loses kinetic energy. That means the charge should not experience any electrostatic force along the direction of motion. That means the field lines must be perpendicular to the equipotential surfaces. So if you draw the field lines for positive point charge, the field lines are this direction. So you know that they are perpendicular to the equipotential surface. Now when you consider the equipotential surface related to overlapping of two point charges, positive charge and a negative charge, you know the field lines will be from positive to negative. The field lines are like this. I already drew it. So if I draw the equipotential surface for this combination of positive and negative charge, the equipotential surface must be perpendicular to the field line. So here it's perpendicular. Then if I consider a line which is perpendicular to the surfaces, so there will be an equipotential surface like this. So we can draw many equipotential surfaces such that they are perpendicular to the field lines. When there is a charged metal plate, metal surface is an equipotential. So if there is a charged metal plate randomly shaped, and if you keep a positive charge here, a point charge here, So metal surface, this is a metal conductor, it's an equipotential surface. So the field line coming out of the positive point charge should fall on the metal, which is equipotential surface, such that the field lines are perpendicular to the metal surface. Wherever it touches, it must be perpendicular to the equipotential surface. The field lines should be always perpendicular to the equipotential surface. The reason delta V is 0, work done is 0, work done 0 means there could not be any component of electric field parallel to the equipotential surface. So field lines should be perpendicular to the equipotential surface. By using this idea, you can draw the equipotential surface if you know the shape of the electric field lines. Okay, so that's all related to electric field. Already I discussed complete lesson on unit 4 related to magnetic field, circular motion, particle physics. I discussed already different videos, around 12 different video lessons for electric field. So that's the reason I revised all those videos as a one video. I thought it will be useful to you. So the link for the particle physics complete lesson, magnetic field complete lesson, circular motion complete lesson will be given in the description of this video, so you can follow it. Also by using the playlist of the channel, you can navigate to any lesson you want. Okay, right, bye.